So this is going to be the last review video covering chapter 7 and 8. So these are two chapters we just took an exam on, so a lot of this information should be fresh in your head. I just wanted to kind of focus your attention to some certain concepts. So once again, I'm going over this final exam review. I'm down in the chapter 7 area, so I'm going to go through a few of these bullet points and show you a few practice examples similar to what you might see on the exam. So kind of following along with this. Don't forget about that practice exam for the final as well. You'll want to utilize both of those as study aids. All right, so we're going to start with temperature conversions. So you're definitely going to see those again. It seems like everyone was doing fairly well in the last exam with temperature conversions. I'm just going to show another example for those of you who would like a refresher. So I'm doing from Fahrenheit to Kelvin. So we have -5 degrees Fahrenheit. We're going to go to Kelvin. Now the reason this is one of the harder ones is because you can't get directly from Fahrenheit to Kelvin. You have to go to Celsius first, and then once you're in Celsius, you can go to Kelvin. So when you're solving this problem, you want to look at your temperature conversion equations. And for this first step, you're going to pick the equation where Celsius is equal to. And then that is Fahrenheit minus 32 over 1.8. And you're going to take this degrees Fahrenheit and plug it in for F. And remember, the key with this equation, parentheses on the top. Do that calculation first. So we have -5 minus 32 gives me -37. I'm going to divide that by 1.8. I'm going to get -21 degrees Celsius. So from there, I'm at Celsius. Next, I need to go to Kelvin. So I'm going to pick the equation where Kelvin is equal to, in this case, it's degrees Celsius plus 273. So I'm going to plug in my degrees Celsius and then add 273 to that. Get 252 Kelvin. All right, so you also need to know how to use the heat equation. So the heat equation is that Q. Q stands for heat. So with this type of problem, you have several pieces of information, as you can see here. So the question I have is how much heat is needed to raise a 122 gram cast iron skillet from 22 degrees Celsius up to 68 degrees Celsius. Okay, so in Celsius, 22 degrees, that's room temperature, essentially. So you're putting it on the stove and you're heating it up. Now here, we're given the C value, which is the specific heat. So Fe is iron, C value is the specific heat, and it's telling us it's equal to 0.215. And for some reason, I feel like that's the specific heat of aluminum. But let's work it through. What matters is how we calculate it, right? Not that the question is accurate. So for this problem, since you're solving for heat, you're looking at Q is equal to MC, and then the delta T, which is change in temperature, so that's final minus initial. So what we're going to figure out is what all these variables are from the equation itself. So we have 122 grams, so which variable does that belong to? Grams is a mass. And in this case, so this is what's special about this heat equation, we want to leave it in grams. All of our other physics problems, we want to convert it to kilograms. This is the exception, just for this one. Okay, so in physics, we want it in kilograms, except for the heat equation. Okay. In chemistry, we want it in grams, but that's a different story and a different review. So our mass is 122 grams. Our C value was given to us in the equation. That's 0.215. And the nice thing about being given the C value is notice it tells you what all your units should be. So it's saying grams is one of the units on your C value, on your specific heat. So that means you want your mass to be in grams. Degrees Celsius is one of the units in specific heat, so that means our temperature needs to be in degrees Celsius. So we have two temperatures here. What we need to figure out is which one is the final and which one is the initial. So it's heating from 22 up to 68. So 68 is going to be our final, and 22 is going to be our initial. So we can plug those values in to our equation. 68 minus 22. Minus 22, and I get a positive 1, looking at 2 sig figs, so 1200 calories. So units are calories, because if you notice from your C value, calories are one of the units on that as well. Okay, so heat is measured in calories. So that's an example of a type of problem using that equation for the final, but looking at some of the concepts with heat. So know what a calorimeter is. So if you remember when we were doing that video where we had 2 styrofoam cups and we had hot water in one cup and we had cold water in the other, and this was during lab, and we mixed the two together. So what a calorimeter is it's a device like a styrofoam cup, that's an example of a calorimeter, that is trying to lessen heat transfer. Okay, so the reason we have styrofoam cups is because we don't want whatever liquid is in the styrofoam cup to lose heat or to gain heat. Okay, we put cold drinks in it because we don't want those cold drinks to gain heat. We put hot drinks in it like coffee because we don't want those hot drinks to lose heat. So it's trying to avoid any heat loss. That's the purpose of a calorimeter. Looking at number 4 under chapter 7, so I'm looking at the review. Definition of heat and the variables that it depends upon. Okay, so heat is this Q value. What variables does it depend upon? Mass. Okay, it also depends on specific heat. And remember, specific heat is dependent upon the type of material. We looked at a table of specific heats with different materials, from water to iron to wood, okay, and they all had different specific heat values dependent upon the material. Because what specific heat is it's the object or the material's ability to absorb heat without changing its temperature. Okay, so how much heat can that material absorb before its temperature is raised by 1 degree? Right, so that's specific heat, type of material. And heat is also then dependent upon your change in temperature. Okay. Definition of latent heat. So we talked about latent heat being the heat that's going into a system during a phase change. Okay, so if we have an ice cube melting, the reason the ice cube's melting is because there's heat going into it, there's heat that's warming it up, but there's no temperature change. All of the heat that's going in to melting that ice cube is going into it changing phase, not into it to change temperature. All right, definition of specific heat, that's the heat capacity of an object, so we talked about that. The 3 methods of heat transfer, so those are conduction, convection, and radiation. And if you look at your final exam review, it asks you to define those as well as give an example of each. And there is a key so that you can compare what you have to the key. So conduction, direct contact. Okay, if I have a poker in the fire, metal poker, and I go and grab it and burn my hand, that is heat transfer through conduction because I am touching the object through direct contact. Convection, this is fluids, whether it be air fluids. Right now, with the weather getting warmer, we all turn on our air conditioning, so that cold air is coming into the room, flowing into the room, and it's mixing with our hot air. And there's heat transfer from the hot air to the cold until the temperature stabilizes. So that is convection, because I have two gaseous fluids, air, mixing together, transferring heat. This can also be with liquids as well, such as if you add cold creamer or milk to your coffee in the morning. Okay, it cools your coffee down because there's heat transfer from the hot coffee to the cold creamer. With radiation, that's when objects are not touching. The sun we used as an example. A fire, when you put your hands by a fire and you can feel the warmth, you can feel the heat. Warming up your food in a microwave is another example. So a few examples of that as well. Moving on, so that is some of the concepts from chapter 7 that you will see. This is not conclusive. There will be possibly other topics, so make sure you're doing that practice exam and looking over past exams. But let's look at 8. So chapter 8, electricity and its properties. So opposites attract, like repel. So remember that in respect to not only electricity, positive and negative charges, but also with magnets. Opposite poles attract, the similar poles repel. So if you have a north and a south, they're going to attract. If you have a north and a north coming near each other, since they're the same, they're going to repel. Okay. Let's move down to Ohm's law. Okay, so you do need to know how to use Ohm's law, and that's that V is equal to IR. So I would look at any example problems that you've had in the past with Ohm's law. Make sure you know how to rearrange this equation as well. But also know how to calculate the resistance in series versus parallel. So let's do split this in half. Let's do series on this side and parallel on this side, because there are some comparisons between these two that you will see. So we have series. First of all, for the resistance, let's draw a picture. What does a series look like? So we have our voltage here. So series is where your resistors are one right after another. You have the same current going through all three resistors. I don't know why I wrote B. It's supposed to be an R. So I want to do an example in kiloohms, because this is how the units you will see it on the final, just so that you can know how to do that. So we have our R1 is going to be 3 kiloohms. Our R2, let's put that at 4 kiloohms. And our R3 will be 8. Okay, so the key with series is same current through all three resistors. Also, the more resistors you have, the less voltage. Okay, so what that means is if these were all 3 light bulbs, and you added a 4th light bulb and a 5th light bulb, the more light bulbs you add, the dimmer those light bulbs are going to be. And that's because voltage is additive. So the more you have, the less voltage each resistor is getting. So those are 2 concepts that are key with series. Now let's look at how to calculate total resistance with series. And the nice thing about series for total resistance is it's just the resistance is additive. R1 plus R2 plus R3. Okay, no real tricks here. So I wanted to do an example with kiloohms because you've only seen it with ohms, so I want you to know that you can calculate with kiloohms too, as long as all 3 resistors have the same units, just use those units. Okay, so for this particular example, resistor 1 has 3, resistor 2 is 4, and resistor 3 is 8. So since they're all kiloohms, Our answer then, when we calculate these, will be in kilo ohms. So I get a total of 15 kilo ohms for my R total. Let's look over at another example with parallel. And I'm going to write this up here so I have a little bit more room to draw my pictures. So what are some keys with parallel? Well, let's draw the picture. So we have our voltage source. And let's do 3 resistors again. Remember, those squiggly lines are my resistors. Now with parallel, it's going to be worth the same. It is not the same current going through all. How much to draw? Because, let me draw a current here in purple. Say the current is going through this way. Okay. Once the current gets here, it's going to split, part going through R1 and the rest going to R2. Okay, so not the same current. Which is nice because then if one of these light bulbs or one of these resistors go out, the rest are going to stay on. So that's the plus with parallel. Also a plus is that the brightness will not change. So if I add 5, 6, 7, 8 resistors, that's not going to affect the voltage because the current is splitting at each interval. All right, so let's do the calculation. So the hard part about parallel is the calculation for your R total, because it's 1 over R total. So if I had 3 resistors, just like I did over in my series, it would look something like this, and I would plug in. I would 1 over 3, and I'm going to do kilo ohms again, just so you can see that you're not changing the number at all, you're just different units. Kilo instead of the base unit of ohms. We have 4 kilo ohms here, and 8 kilo ohms. Now I know this might be boring you because you just did this one. So 1 divided by 3 plus 1/4 plus 1/8. So my 1 over R total is 0.708, so on and so forth. Okay, this is not my R total, this is my 1 over R total. So I need to do my inverse button, my x minus 1, flip that, and get my R total then of 1.4 kilo ohms this time. All right. So, other than some Ohm's law equations, Chapter 8 has a lot of concept equations, which I just talked about here with series and parallel circuits. So I would review the concepts as well as the calculations. For the final exam, there is 50 questions and 8 chapters. And we try to make it pretty even. So you're looking at approximately 6 questions per chapter. Okay, so we obviously can't cover all of the topics. So pay very close attention to this review that I posted. Watch the videos that will be most helpful to you, if not all of them, and then do that practice exam. All right, let me know if you have any questions. If there are any areas that you're not feeling confident in, please contact me. We will set up a Zoom review. It's got a whiteboard on it that I can work problems with you and answer questions with you in real time. So the exam will be going up on Thursday, which is tomorrow my time because I'm making this video on Wednesday, so Thursday the 7th, and it will close midnight on Monday the 11th. So good luck and let me know if you have any questions.